When you first begin to exercise, you notice a big burst in your energy. After a while, around 24 to 27 hours, you get something called DOMS, which is delayed onset muscle soreness. This makes your body extremely sore, especially if you have not worked out in a while. After working out a couple of days in a row and keeping a good diet, your body will begin to produce more mitochondria through a process called mitochondrial biogenesis.
You can easily train yourself to listen faster.
Training log, day 14.
Last day, day 14 of the inactivity period.
It has been 2 weeks since we've done any exercise.
I've been quite tired.
And you'd think that conserving all this energy for 2 weeks, you'd have more energy, but that's not the case. Well, let's take a look back, 14 days.
So we're on our way to the clinical nutrition department here at the university to do a little chemistry experiment. We want to find out how our body's use of energy is related to the amount of exercise we do.
First, let's explain the basics of energy. Energy cannot be used up, just converted into different forms. The food we eat contains chemically stored energy in the form of energy-rich molecules, such as carbohydrates, proteins, and fats. When we do physical activity, these large molecules are first broken down to smaller molecules, such as glucose, that are transported to the muscles. Oxygen, which is also needed in this reaction, is transported from the lungs to the muscle, where it reacts with the glucose, producing carbon dioxide and water, and a small molecule called ATP, which is our body's energy currency. But we often hear the term calorie or kilocalorie when we talk about energy in food. A kilocalorie is actually a way to measure energy, and it's defined as the energy needed to increase the temperature of 1 kilogram of water by 1 degree Celsius. And to understand the meaning of this kilocalorie term in relation to how our bodies work, we are going to do a little chemistry experiment.
So the experiment you're going to perform right now is that during 2 weeks, you're going to be as passive as possible with as little exercise as possible. And then during 2 weeks, you will exercise as much as possible. And then we will see how big the difference is in energy expenditure.
So this is how we can do this. First, we drink a dose of so-called double-labeled water. It's normal water, except that both the hydrogen and oxygen atoms are isotopes of their normal form. An isotope has the same number of protons in the core, but differ in the number of neutrons. This water will then mix with the water we already have in our bodies and follow the water's normal pathways. All the marked hydrogen will go out with the urine together with some of the oxygen. The trick is that we will exhale some of the marked oxygen as carbon dioxide, and we will exhale more carbon dioxide if we train. Quite simply, because we breathe more when we train, right? So depending on how much labeled oxygen and hydrogen we can detect in our urine, we can also calculate how much energy we have used.
So first, we wanted to investigate our energy expenditure during rest, which meant doing everything we could to do as little exercise as possible, but still live a normal life. No, seriously, this isn't training. And then it was time to drink a new dose of double-labeled water and begin 2 weeks of hard training. And to help us do that, we have our very own personal trainer, Moa Nilsson, at Fostra.
Okay, so we're done with 2 weeks of training. Now it's time to compare the results.
The chemical analysis of the double-labeled water from our urine samples showed that I went from using around 2,500 kilocalories per day during inactivity to around 3,800 kilocalories during weeks of training.
And I went from using about 3,000 kilocalories per day to about 4,700 kilocalories per day.
Well, if we start with the inactive period that you had, we can see that you had a very low energy need and you had very little physical activity. And that is shown to increase the risks of several diseases like heart diseases, cancer, overweight, and obesity.
It may be obvious that the total inactivity option is not recommended. But what I found really interesting is that we can use chemical isotopes of hydrogen and oxygen and water to put a number on how many calories or chemical energy our bodies simply need to function and to do hard work. And it turned out that saving our energy by doing hardly any exercise at all actually made us even more tired. Why do you think that is?
A chemical experiment, like the one we just did, can give us valuable information concerning physical activity, different lifestyles, and our overall health. But chemical research related to sports is so much more than this. For example, a lot of biochemical research is done to understand how our bodies make use of different sources of energy and how this may change during, for example, long-distance training. Studying and understanding oxygen uptake and transport help athletes train more efficiently. And chemists are also working to come up with improved materials in sports equipment. So get out there and burn some chemical energy. Just remember to eat right as well. Because you know, chemistry is all around you and inside.
All right. Why do we need more mitochondria in our body? Mitochondria is essential to our body when we exercise. Your body begins to run out of energy after only a couple minutes of working out. And when it runs out of ATP, mitochondria begins to break down carbohydrates, proteins, and fat through the process called fatty acid oxidation. Fatty acids are converted to acetyl coenzyme A, which are then oxidized for energy production. When exercising, your body creates many chemicals that benefit your body at that moment and sometimes benefit your body on the long run. Chemicals released when exercising. When exercising daily, your body begins to release a chemical called endorphins. Endorphins interact with your receptors to reduce your perception of pain. These chemicals also relieve stress. Dopamine may also be released when working out. Dopamine is released when you reach a goal and it makes you feel motivated. One thing that I found something I didn't even know about is where your fat goes when you burn it. When you burn fat, people may think it might turn into energy. However, the laws of chemistry, the conservation of mass, which is that mass cannot be created or destroyed, says otherwise. The actual way you lose fat is by your fat being converted to carbon dioxide and water. The carbon dioxide gets exhaled and the water mixes in your circulation where it comes out of your urine or sweat.
That's a Chromebook with built-in virus protection, so you can click with confidence. With no more of this, and a lot more peace of mind. Move along, viruses. Switch to built-in virus protection. Switch to Chromebook.
There are some things in life that when they're around, we wish they weren't there, and when they're gone, we're just glad they left. For many of us, one of those things
is fat. But your fat tissue is full of important biological molecules called lipids, long stringy compounds of hydrogen, carbon, and oxygen that are great at storing energy in their chemical bonds. When the molecules are broken apart, they release the energy stored in their bonds. We often refer to this process as burning fat. But when you burn fat, where does that material, the actual stuff that jiggles around and cushions you and insulates you, where does it go? Interestingly enough, a recent survey of doctors, dietitians, and physical trainers revealed that even the experts in fat loss didn't know the answer, although they thought that they did. More than 50% of the respondents thought that when you burn fat, all that mass is simply converted into energy and lost as heat. It's a common misconception, but it's not possible. I mean, just because you don't like something doesn't mean that the laws of chemistry don't apply to it. And one of the basic principles of chemistry is the conservation of mass. This just means that the same amount of material always comes out of a reaction as goes into it. Even if that reaction happens to generate heat, you'll wind up with the same number of each kind of atom that you started with. So when you break up those lipids in your fat cells and release their energy, all of that hydrogen, carbon, and oxygen in those molecules will still be there afterward. But if you burn a lot of fat and it's not there anymore to hold your pants up or whatever, where did the mass go? Turns out you exhaled it. Biologists at the University of New South Wales recently did an atom-by-atom breakdown of where the mass of your fat goes after it's burned in your body. They found that for every 10 kilograms of fat that you burn, you have to inhale 29 kilograms of oxygen to metabolize or break down the fat and release its energy. And the process of breaking down that much fat produces 28 kilograms of carbon dioxide and 11 kilograms of water. So for every kilo of fat that you burn in your body, more than 80% of that mass is lost as carbon dioxide that you breathe out. The other 20% you lose as water in your urine, your sweat, or depending on how hard you work out, your tears. But if you do the math, you'll see that all the mass in that fat burning reaction has been conserved. 10 kilos of fat plus 29 kilos of oxygen equals 39 kilos total. And together they produce 28 kilos of CO2 plus 11 of water, which also equals 39 kilos. So remember that the next time you're huffing and sweating on a treadmill or walking your dog or really doing anything that makes your body call on its energy reserves. You're basically just emanating fat through your breath and your skin, but in a good way. Thanks for asking, and thanks especially to our subbable subscribers.
All right, and then that would be all. There's my bibliography. Any questions?